Okay, so this is the second part of the lecture on regularization. So we've talked a bit about, in the first part, we talked about regularized linear regression. We talked about different types of regularization, particularly L0, L1, and L2 regularization, how L0 regularization gives you sparse solutions, but is kind of computationally harder. L1 regression is computationally easier because it's a convex optimization problem, and it also tends to give you sparse solutions. And L2 is not only convex, but actually has an analytically tractable solution for moderate sized problems, but it doesn't give you sparse solutions. It gives you less sparse solutions. So just want to, if we can maybe get some insights into the way these penalties affect the estimates of the parameters, the regression coefficients. And one way to get some insight is to look at some special cases where there's some simple results. And so the simplest special case where you can actually get analytic results is where the predictors are independent of one another, or more formally, where the columns of the predictors, the columns of X, are orthogonal and orthonormal. Okay, so in that special case, so that that has to be in the case where P is less than N, right? They can't all be orthonormal if P is bigger than N. So, but just to get some, I mean, very often these methods are applied when P is bigger than N, but to get some insight still, it's helpful to think about this case where X is orthonormal, because they then have explicit solutions in terms of the ordinary least squares estimates. So here, okay. So what are those? So those explicit solutions are given here. So for L0, what this equation here means, the I is the indicator, it says that the L0 estimate of beta here is, I guess I was using B before, sorry, I switched to beta. So the L0 estimate of beta is just the least squares estimate, beta hat j, if beta hat j exceeds some threshold, this beta hat m, and it's 0 otherwise. So essentially what's happening here is that the L0 penalty simply thresholds the ordinary least squares estimates. All the ones that are bigger than some threshold you keep, and all the ones that are smaller than some threshold you throw out, you set them to 0. So that's the form of the L0 solution in that special case where X has orthonormal columns. So what does the threshold depend on? Well, the threshold depends on the strength of the penalty, right? So the penalty is very strong, then you throw out everything. So the threshold will be very small. And if the penalty is weak, then you don't threshold anything, and the threshold's very, sorry, in this case, I guess that not thresholding anything would be, the threshold's very small, you keep everything, right? Threshold in the penalized case, if the penalty is strong, you set them all to 0. And the threshold, the beta m here, would be very big. Okay. What about the L1 solution? Well, essentially what happens here, if you think about this, what this says is essentially take away lambda from the ordinary least squares estimate and take the positive part of that. So if your estimate is bigger than lambda in absolute value, you basically just subtract lambda from it, or subtract lambda from its absolute value. Whereas if it's smaller than lambda, you set it to 0, because if it's smaller than lambda in absolute value, after you subtract this lambda from it, the positive part is 0. So I'll draw a picture in a minute, but let's just talk about the L2 case. The L2 case essentially just divides all the least squares estimates, the beta hat j, divided by 1 plus lambda, where again something positive. So this is dividing them by something bigger than 1. It makes them all smaller, okay, by some kind of constant shrinkage factor. You can think of this as shrinking the betas towards, makes them all smaller. When I say smaller, I mean that makes them closer to zero, right? The positive ones become close to zero. The negative ones get close to zero too. So maybe we can have a picture. Okay, so if we plot the for L0, sorry, L0, if the x-axis is the ordinary least squares estimate, remember what it did was it set all the ones which are smaller than some threshold to 0. And that threshold was in absolute value. And then the others, it leaves alone. So if this is, sorry, I wasn't very good, but this was supposed to be y equals x. It's supposed to go through the origin. There's y, there's x. And so what the L0 penalty does is it leaves alone the coefficients that are bigger in absolute value than some threshold or smaller than absolute value than some threshold. And then the others it sets to 0. So that's what that's why it's called, it's sometimes called hard thresholding. Basically, the L0 has this feature that so you can think about it, compute the least squares estimates, and then all the ones which are bigger than a threshold keep, all the ones that are smaller than a threshold throw out, okay, set to 0. So again, this is only in the special case of orthonormal predictors, but it kind of gives you some insight into what the L0 penalty is doing. If we go on to the L1 penalty, so same again, maybe I'll try and get through the origin a bit better here. So y equals x. So y here is the shrunk estimate or the penalized estimate. Maybe I should have. And this is the ordinary least squares estimate. So again, you can think about it. The L1 solution in this special case also is being based on compute the OLS estimate and then apply this, what's actually called the soft thresholding operator, which if you remember was if it's less than lambda, it's going to get set to 0, the estimate. If it's more than lambda, you subtract lambda. So after lambda, it gets small, all the estimates are smaller, closer to 0 than the original by a constant amount, lambda. And lambda, of course, was the penalty, right? So if lambda is 0, you just get the ordinary least squares estimate. If lambda is infinite, everything gets set to 0. Okay. And this is called soft thresholding sometimes. This idea of subtracting lambda, and if it's smaller than, if that gives you something, subtracting lambda from the absolute value, if that gives you something smaller than 0, set it to 0 if it doesn't keep that subtracted value. This was called hard thresholding. And then L2, you get a plot like this. It doesn't have this thresholding. So this is y equals x again. It doesn't have this thresholding thing. It still makes things smaller but by a constant multiplicative factor. So you get something like this, where if I guess if lambda is very, very strong, everything gets shrunk very strongly towards 0. If lambda's less strong, you still get a linear dependence. And if lambda's very, very weak, then I guess you get something very close to y equals x. So the slope of that line depends on lambda, okay, depends on the penalty. So that's the qualitative behavior, and you can kind of see, again, in this feature, you can see why maybe the L0 produces sparse estimates in this special case. L1 does as well because of the thresholding, and L2 doesn't, right there. None of this makes everything a little bit, the OLS estimates all a bit closer to 0, but it doesn't set them exactly to 0. So that doesn't give you sparse estimates. Okay. So that's summarized here. So why does the L1 penalty produce, what's the, in fact, I mean, although I've just given you the analytic solution for a special case, in fact, it's generally true that the L1 penalty produces sparse solutions. And there's a, that's here, there's a geometric picture we can draw again. So going back to the picture, this is a, forget that this is no longer that special case. This is completely general. But let's, now I'm going to, instead of, I'm going to plot a new, just think about the regression in 2 dimensions. So a 2-dimensional regression. So this is beta 1 or B1. So we've got 2 predictors. Two predictors. So there's a different axis now, different kind of plot than I was plotting before. Okay, thinking about those 2 predictors, and think about the L1 penalized regression. Remember that it can be also thought as a constrained regression, or so let's think about it in terms of a constraint. So it kind of gives you a different geometric version. So this square here, this diamond, maybe I should say, is the constraint that the L1 norm of beta is less than or equal to some lambda. I should use C, I guess, for the constraint version. Okay, so that's what that constraint looks like. It's like this diamond shape. And now remember what the least squares criterion looks like. It looks kind of like, well, maybe elliptic contours or circular ones, depending on whether we scale things. But okay, let's imagine we have elliptic contours here. So what we're trying to do is minimize this least squares function. Let's suppose this is the global minimum, and then the contours are going up. So we're trying to minimize this least squares function subject to this constraint, it lying in this space. Okay. And what you can see intuitively is that if the first place that these elliptic contours here, if the first place they touch the constraint spaces on this is at a corner here, then that corresponds to a solution in which one of the betas, in this case beta 2, is 0. It's a sparse solution. So the idea is that these corners of this constraint space correspond to this, quote, sparse solutions. Now, of course, we're only drawn it in 2 dimensions. So a sparse solution is, where one of them is 0. But you can think in more broadly, the kind of, even in 3 dimensions, think of the constraint on beta 1, beta 2, beta 3, the constraint that the L1 constraint is kind of a spiky constraint, which has these these corners to it. And it's because of that kind of spikiness, if you like, these corners, that it's not unusual for the elliptic contours to hit that constraint space at a corner instead of on the edge. Of course, it is possible for it to hit it on an edge, and then you've got a non-sparse solution. But in high dimensions, there's lots of corners basically in high dimensions, and so this constraint it's very likely that the elliptic contours will hit somewhere on a cornerish part where only a subset of the coefficients are non-zero. So that's a geometric view as to why you get a sparse solution. If you think instead about the L2 constraint, the L2 constraint is a circle, right? So it doesn't have any corners. And so you're much more likely that with probability 1, essentially, the elliptic contours are going to hit somewhere along that circle that's not on the axes labels. So it's exactly this geometric reason why the L1 constraint, which has this, like these corners, that's what produces the sparsity. So if you have other constraints, you could imagine constraints like this, right? These would also produce sparse solutions. But this constraint space here that I've just drawn is not convex. And so it makes the computation harder. In fact, this is closer to the L0 kind of constraint. It's not quite the way I've drawn it, it's closer to it. So the reason that what you get is that the L1 constraint here is like a compromise. It's got the corners, but it's convex. And that's one reason it's been so widely studied is because it produces sparse solutions, but also does so by solving a convex optimization problem that's super easy to solve. Okay. Okay, so there was just, I guess there's a couple of, I wrote these couple of practical dots here, bullet points, just to say that, you know, I wrote this regression without maybe an intercept here. So one of you could add an intercept here, maybe a mu, or you could think of one of the columns of X being an intercept. But so there's an issue here that you don't want to penalize or constrain the intercept in the same way usually as you want to penalize the other predictors. So the intuition is that those other predictors are kind of comparable to one another in some sense. So their B's are kind of comparable to one another in some sense, and you might want to constrain them comparably, whereas the intercept is kind of a special term. So usually what people want to do is fit this model where the coefficient for the intercept, let's call it mu, is unconstrained or unpenalized, and only the B's are penalized. And actually, it turns out you can do that by simply centering the y vector, that is subtracting the mean of y from every observation so that y has mean 0, and centering the predictors, the columns of X, so that those have mean 0 too. So that's a common trick that people use in practice to fit this model. So the idea is that that's important. It essentially means that I should have had here on my bullet, center y to have mean 0, but also center X to have mean 0, center the columns of X have mean 0. That's equivalent to fitting, it turns out that the B's that come out of that are equivalent to fitting a regression model with an intercept, but where the intercept's not penalized or not constrained. The other issue is that in order for it to make sense to constrain the B's in the same way, this kind of, these symmetric constraints, we've got, adding up the absolute values of the B's or adding up their squared values, they have to be comparable in some way, the different predictors. And usually that means they need to be on some scale that's comparable. So if you think about the regression of house prices and you're regressing it on the number of floors and the square footage, so the coefficient of the number of floors, its interpretation, its kind of units is per floor, whereas the interpretation of the coefficient of the square footage is per square foot. And so it doesn't really, those two units aren't comparable with one another. So to make the betas, if you're going to penalize things by the sum of the squared values of the betas or the sum of the absolute values of the betas, you really want those betas to be on the same scale. So when you're dealing with X predictor variables that have completely different units, the standard thing to do is to standardize the X's to have unit variance. So center them and standardize them, divide by their standard deviation. So then the units of beta are kind of per standard deviation of X. Okay, so that's another kind of detail that you need to worry about. Actually, I mean, most software that fits these models does that for you automatically because it's so common to want to do that. So the only time you might not want to do that is if you already know the X's are kind of comparable to one another in some way. So in some problems I work on in genetic data, the X's are genetic variants. And in those cases, you could say, well, a change in a genetic variant, in the first genetic variant, you might think of that, a difference in a genetic variant being comparable with the difference of another genetic variant, even if the genetic variants don't have the same frequency. So even if the genetic variants don't have the same variance in terms of because they're kind of binary or binomial variables in terms of the X's. So standardizing them might not be necessary. Actually, it's kind of a subtle question whether you should standardize them or not in that setting. But if the X's are things that are not comparable with one another, like numbers of floors and square footage, you really want to standardize before doing this. Another way of thinking about it is you don't really want the units of measurement of X to affect the answers you get. So if you change from square feet to square meters, you wouldn't want that to change your answer. And, you know, if you standardize X's before you apply these methods, it has the property that it doesn't matter what units of measurement you use. Okay, so just those are details in terms of actually using the methods. As I mentioned, the GLMNet, for example, in R takes care of all that kind of thing for you, but just to be aware that it's doing that. Okay.